Hi everyone, this is our second part of the lecture, and this part is concerning with AC bridges. In this lecture we will study different bridges that are used for impedance measurement, and in impedance we deal resistance, capacitance, which is from the capacitive impedance, so capacitance, and inductance, which is from inductive impedance. So we will calculate these things in terms of a known or some known quantities. Also we will study some bridges that are used for calculating the frequency of a circuit or the quality factor of their circuit or power factor of their circuit. So bridges are used for these things in AC circuit. In DC circuits we have bridges only for impedance measurement, resistance measurement, but in AC we are having these much quantities. So we will have some introduction with the basic concept of bridge, and then we will derive an equation for impedance bridge, Maxwell bridge, Hay bridge, and we will also study some different bridges, other bridges that are used for doing the same things, these same things. And after that we will study the frequency measurement techniques using Wein's bridge. So these are our today's topic. AC bridges or alternate current bridges are popular for its measurement purpose, and we measure the unknown inductance, capacitance, of course resistance, and related quantities. These bridges are derived from conventional DC Wheatstone bridge. So Wheatstone bridge had a structure like this, that it had it had 4 resistances and a galvanometer, and it had the applied voltage as a DC source. So a DC can only measure resistance. So this is the general bridge, Wheatstone bridge, and this bridge is then modified for AC circuitry by replacing R with, which is a resistance, with impedance Z. So Z is the combination of R and some quantities of XL and some quantities of XC, so XL minus XCJ. So anything in these can be 0, and even resistance can be 0, which will make an AC bridge. So this means that XL, which is J omega L, and XC, which is 1 over J omega C, these both quantities require a frequency omega, which is omega equal to 2 pi f. So f is the frequency with which this circuit is being excited. So the DC bridge is then converted to a sort of AC bridge. So the first modification is that we have an AC source in here. So this is Z1, Z2, Z3 and Z4, and this galvanometer is used for DC here. So here this thing is known as the detector, and this detector can be of various types. So normally for the frequency with which our vibration galvanometer works is 5 Hz up to 1000 Hz, and they have highest sensitivity when operating for frequencies below 200 Hz. So when an instrument is of lower sensitivity, it will give you a bit wrong reading, in bold words. So we can also use some audio devices and amplifiers for checking this potential between these 2 points. Normally the process is that if the potential between these 2 points, point B and point C, is 0, the difference between these 2 points voltages is 0, then we say that the bridge is balanced, and at balanced condition we can define some balance equations. So that's why we need a detector to check if these 2 points are having same potentials or not. So headphones or audio amplifiers are used for above to 50 Hertz frequency, and even at 3 kilohertz and 4 kilohertz these audio headphones are useful. Transistor amplifier with frequency tuning facilities can also be used for detecting this balance condition, and in that case if the transistor amplifier is tuned with the frequency, then we hear some beats. So beats are the disturbances which are heard if we are having same frequency with different closer frequencies to one another, so we hear beats. So let's say one frequency is 2 Hertz and 20 Hertz, and the double of this frequency is, let's say, 40 Hertz. So we divide this 20 up to 40 into 12 intervals. So if we go from interval 1 to 3, we do not hear beats, but if we go from interval 1 to 2 and we play these two frequencies with one another, so we hear beats. So closer frequency will give you beats, and the wider frequency will not give you beats, and same frequency, of course, it will never give you beats. So this phenomena is checked for higher sensitivity based circuitry. Okay, now coming towards the impedance equation for a balanced bridge, we previously discussed this circuit, so it will be a bit easier now that we are having 2 points across which we apply the AC voltage, and we have 2 points across which we check the potential difference if it is balanced or not. So this thing is the detector. Okay, so at balanced condition, what we see is that this voltage is equal to this voltage. So we can say that the voltages, this at here and at here, is same. This voltage on this point is total voltage which is given from this circuit, but after the drop in Z1 and in Z2, if these both potentials are same, we can say that V1 is equal to V2. So V1 is equal to V2 when the circuit is balanced and we hear no beats, we hear no deflection on the, we see no deflection on the galvanometer. So in this condition, we can say that I1Z1 is I2Z2, and we also note that I1 is equal to I3 because no current will flow in this at balance condition, since the potential around these 2 points will cancel out one another because of their same sign and same value. So I1 is equal to I3. This is I1 and this is I3. Both are equal to this total voltage which is applied across this thing divided by the total impedance of the path. So impedance of the path is Z1 plus Z3, or V divided by Z2 plus Z4. So both are correct. So I1 equal to I3 is equal to V divided by Z1 plus Z3, and I2 is equal to I4. This 2 is equal to 4. 2 and 4, they are equal. So they are equal to V divided by Z1 plus Z2. Now put the values of I1 and I2 from these equations in it. So we put this thing here and this thing here, and we got V divided by Z1 plus Z3 into Z1, and V divided by Z2 plus Z4 into Z2. So this V cancels out with V, and if we multiply this Z1 with this and Z4 with this, we get Z1 Z2 Z1 Z4. And similarly with Z2 we will multiply Z3 and Z1, so 1 2 and 3 2, so 1 2 and 3 2. So we got this equation. Now if we see this equation, the 1 2 is cancelled out with 1 2, and we are left with Z1 Z4 equal to Z2 Z3. So if we move this thing here, what we will get Z1 by Z2, and move this thing here, we will get Z3 divided by Z4. So this is our balance condition equation. If we convert this equation to an impedance form, so in impedance we just move this Z1 here and Z2 here, so we get 1 divided by Z3 and Z2 equal to 1 divided by Z4 Z1. Now this is 1 over Z3 and 1 over Z2, so 1 over Z is Y, so 1 over Z3 would be equal to Y3, 1 over Z2 would be equal to Y2 equal to Y1 Y4. So this is the equation 2314 in term of admittance. So admittance is from the 1 over Z, from 1 over impedance. Now this was the whole story. This is a general equation for a balanced bridge in term of impedance. Now we can formulate these impedances in capacitance and inductances to get our desired values for capacitance and inductance and even frequencies, because we can also plug in values for calculating frequency. So this was the story. Equation for general impedance at balance condition can be explored as Z1 Z4 equal to Z2 Z3. These things are phasors. So phasor is having an amplitude and an angle. So in general resistance, R1 R4 equal to R2 R3. In this case we always have zero angle, so angle theta is always 0 degrees. So the theta does not matter in DC bridge, but we are now working with AC. So in AC, this Z1 is actually Z1 angle theta 1, Z4 angle theta 4 equal to Z2 angle theta 2 into Z3 angle theta 3. So angles will add up in phasor. Why these angle will add up? Because it is actually Z1 e power j theta 1 into Z2 e power j theta 2. Let's say one angle is 1 and one is 2. So what will happen? Z will multiply with Z, Z1, Z2, and E will add up. So e power j theta 1 plus theta 2. So these thetas would add up to give 1 plus 4 and theta 2 plus 3. I hope you have understood this procedure, that why thetas are added and amplitudes are multiplied. Why these are added? Because amplitudes are actually from the first part, the coefficient part of the exponent, and the theta is from the second exponential part of this E. So A into B and E is common, theta 1 plus theta 2. So this happens in here. So Z1 4 and multiplied and theta are added. Similarly 2, 3 are added and multiplied for amplitude and phase conversion. Okay. The first condition is that the magnitude of the impedances must satisfy this equation. So now we are having two conditions in this circuit: the amplitude wise or the magnitude wise condition, and the second one is the phase wise condition or the angle wise condition. So we must have Z1 4 equal to Z2 3, and we must have theta 1 plus 4 equal to theta 2 plus 3. So these two relation must be satisfied for a balanced AC bridge condition. Now let's deal an example on this. So we are having an AC bridge, and this AC bridge is shown in this figure. This is figure 6.1. okay, and this thing was wrong in book. It is microfarad, but here it is written as millimicro. So millimicro is nothing. Okay, we are supplied with 20 volts at 500 hertz. So this is our source power, source voltage, and the arm wise impedances are given. AB is 0.25 microfarad. AB is 0.25 microfarad. Now remember that this thing is capacitance and not XC. So we will convert it to XC by 1 over j omega c method. Okay, the BD is an arm. BD is actually this side. So BD is 400 ohm. This is already Z. So we are good with this Z3, but Z1 must be calculated. Okay, and the AC is having 120 ohm. So again AC is this arm AC, and it is Z2. So we are good with Z2 and Z3. And find the resistance and inductance or capacitance of CD. So CD is actually our Z4. This is our CD. So this is to be calculated, and then we will be calculating the mixed value of Z4. Means it will have some real value plus some imaginary value. So it will be a complex value, and then we will separate real and imaginary to get our resistance and capacitance or inductance. It can be positive or negative. So we will then find that what is this thing. So this is the whole story. So first of all, this first branch is not in impedance, so convert this thing to impedance. So for that we use this frequency given, Z is equal to 1 over j omega c, 1 over 2 pi fc, and it turns out to be 1273 ohm. So now Z1 is solved, and since it is it is capacitance, so it will have a 90-degree minus with it, because there was a j in denominator, and 1 over j is equal to minus j is equal to minus 90 degree. Okay, so now this thing is done. If we apply the balance condition in here, so the balance condition would be here is another thing. This 120 ohm is in parallel with another 0.15 microfarad capacitance. So this is not only 120, it is in parallel with an XC2. So for that we will first find this XC2, which is in parallel with it. So we will use the parallel equation for it. So parallel is that 1 over R1 plus 1 over R2 is equal to 1 over RT. The shortcut of this, if you are using a calculator, would be that the total Z would be, first you will write one value and take its inverse, and then you will add another value, let's say X, and take its inverse and make it equal, and then again take it inverse. So this is the shortcut for the people who use calculators. So you put value, you take its inverse, and you add another value and take the value of that values inverse as well, and then total inverse. So A inverse, B inverse, whole inverse. Okay. So after that we got this Z2 equal to 119.8 with a very small angle of 3.2 degrees. So what we did is that we calculated Z4 using this equation, and Z4 turned out to be 37 angle 86. So we are having two components of this. The first one is R, which is 37 cos 86, degree, and second one is x, which is 37 sine of 86 degree. So this will give us some values, and it turned out that this second value was positive. So positive value means that it is an inductor. So we will compare this value, the second value. This first one will give us the resistance. The second value will be compared with j omega L, sorry, and this L can be calculated afterwards as total value divided by 2 pi f. So 2 pi f is this, and we got 11.97 millihenry. So this is it for the balance condition of an impedance based bridge. Okay, now let's explore the same bridge for some phenomena where we calculate the capacitance and inductances. So Maxwell bridge is used for calculating the inductance, and it's a bit simple, because what we have is that we are having a variable inductor and a variable resistance in it, and we just use the balance condition of Z1 divided by Z3 is equal to Z2 divided by Z4, and we put the values of these things. So Z1 is R plus J omega L1, R plus J omega L1, and Z3 is only R, so divided by R, and Z2 is this one, so R2 plus J omega L2, R2 plus J omega divided by R. So if we solve this equation, it turns out that we get the same resistance base for real components, and in J omega L1 equal to J omega L2, R2, R4. This is the imaginary value base. So this equation is actually compared with this one, and this is compared with this one, because it has a J and it has a J. So we got two equations, and then we can calculate our L2, because L2 is here. Sorry, we can calculate our L1 in terms of this L2, R3 and R4. So if we have variable resistances and a single variable inductance, you can calculate the unknown inductance with it. Maxwell inductance and capacitance bridge is used for calculating inductance in terms of capacitance. So in first Maxwell bridge, we had two inductors on the same side of the bridge. So if we do not want to use this one, we can just replace this thing by a capacitor on the opposite branch. So that capacitor is introduced in parallel with this circuit. And now if we calculate these values, so what will happen, this R1, R2 would be same, but the second equation would have a capacitance in it. So this capacitance is giving us L1. So this is the difference between Maxwell inductance capacitance bridge and Maxwell bridge. In capacitance bridge, we use an opposite side capacitor with the inductor. Okay. The advantages and limitation of Maxwell bridge is that Maxwell bridge is requiring C4 and R4, which can be varied independently. This is the advantage of this one. In the previous bridge, there is no separate inductance, because inductance is always connected with resistance, so both things vary simultaneously. Okay, and after that the final balance condition are independent of frequency, and frequency can use any frequency we can use for this circuit. Balance condition is dependent of losses with inductor, because in balance condition we are having no inductance connected, so it is independent of inductor. And wide range of inductance at power and RDO can be measured, because it does not depend upon frequency, so we can use it on any frequency. The disadvantage is that the capacitance that we are using is very expensive. and rest of the advantages are with quality factor. So quality factor is very low for such circuit because we are using lower frequencies, and low value of frequencies have a bit wider bandwidth, so that's one. Okay. Now coming towards the Hay bridge. Hay bridge can be remembered as Henry's bridge because it measures our inductances. The procedure is same, but the structure is different. We are having same branch as this one, but we want to calculate L now. In this bridge we are having a variable capacitance in series with it. So in previous one it was in parallel, and in this it is in series. What makes this thing different is that the first thing is that it requires the frequency. So we must have a frequency, constant frequency, for measuring or operating this circuit. And the second thing is that it can calculate the quality factor of the circuit as well. So this can be used for calculating the quality factor as well. The rest of the things are same for this. Other bridges include the Anderson, Owen, the Sorties and sharing bridge, and these are the quantities that can be measured with this. So just go through it and let me know what's your opinion on it. Okay, the frequency measurement is a bit different topic. First we were calculating inductance and capacitance and resistance, but now it is frequency. So for frequency, the parallel circuit of capacitance with resistance is used on its first branch, whereas a series circuit is used on this branch. So if we compare this thing and equate real with real and imaginary with imaginary, we get these two equations. This one is for real component, which is of no use to us, but this one is 2 pi 1 over C1, C2, R1, R2. So this C1, C2, R1, R2, if these are kept same, we get C into C, C square, R into R, R square under root, which is R square RC. So this frequency can be calculated by F is equal to 1 over 2 pi RC in this bridge. And this is it for the Wein's bridge. Wein's bridge is used for calculating the frequency. So we do not need to have the known frequency for it, and we should have R1 equal to R2 and C1 equal to C2. And if we balance this thing at that balance condition, we will get what? The good frequency with which it is being operated. So this is it for the chapter on bridges. I hope you people have an idea on the bridges after reading these different types of bridges for calculation of various electrical terms. Thank you.